Hey everybody! In this video we are going to find the curve length of a curve in polar coordinates. So let's take a look. Here is our formula for curve length down here. Now this is just some background information that needs to be true in order to use this formula, so let's talk about it real quick. Our curve is a function of our angle theta. We have to have a continuous first derivative between the two angles, alpha and beta, that we're looking at on our curve. And then the point r comma theta has to trace out our curve exactly once between alpha and beta. So basically we're not like repeating loops or anything on our curve. If all of that's true, the length of our curve between those two angle values is this integral right here, where our integrand has square root of our function r squared plus its derivative squared. So let's work out an example. We want to find the length of the cardioid r equals 1 minus cosine theta. Now we don't have to look at the graph to use that formula, but I do want to show you. So the very first thing I'm going to do is just to find a handful of points that would be on the graph, and then also recognize that this graph would have symmetry about the x-axis. We went through this in a previous video, how to check for symmetry, and so I only need to plug in a handful of points and then I can reflect my graph to get the rest of it. So here's what that cardioid looks like. And let me line up a few points for you. When you plug in 0 for theta, r is 0, so that point would be right here. When we plug in pi over 4, that would be about right here roughly, okay? So we're basically tracing out our curve. Okay, so we're about right here when pi over 4 gets plugged in. At pi over 2, we're up here at 1. 3 pi over 4, we're up here at 1 plus square root 2 over 2. And then when we plug in pi, we're over here at 2. So what I want you to recognize is if I keep going and plug in more points, it's just sweeping out the rest of this curve. And I would get to this end point, I guess you could say, when I plug in 2 pi. So our curve is traced out exactly once as we go from 0 to 2 pi. So there's no overlapping or anything. So then we're going to go to our length formula and fill in everything that we know. We know r, it was given to us. We just figured out alpha and beta, and then we just need to find the derivative of r. So here's r. Take the derivative of this with respect to theta, and we get sine theta. And so plug all that into our formula, and we have this integral. And then the rest of this is just going to be simplifying and then eventually integrating. So we have a binomial squared right here that we're going to have to FOIL out, and then we have sine theta squared. And notice the limits of integration go from 0 to 2 pi. So then if I FOIL out the first binomial, we have this integrand, and then notice something. What's this? Hopefully that looks familiar. That's just 1. So cosine squared plus sine squared is your Pythagorean identity. So I'm going to add that one with this one that's already in the front, which gives us a 2 in the very front here, and then just minus this 2 cosine theta. Now, at this point, what I have to do is I have to reference some trig identities that I've learned in the past and see what can be useful here. And a lot of times you might have to manipulate your trig identities. This is one that you probably have on some kind of chart or you've referenced it a lot. So we know that sine squared theta is 1 minus cosine 2 theta over 2. Now I chose this one for a reason. It doesn't quite look like what we have going on, but it will in just a moment if we do just a little bit of manipulation. So why I chose this is because of the fact that it has a something minus cosine theta. I know it's a 2 theta here, but we'll address that. If I multiply both sides of this identity by 2, I have 1 minus cosine 2 theta. And then now how do I get just a regular theta like I have right here in my integrand instead of a 2 theta? Well, I just adjust accordingly on both sides of my equation. So take a look. If I want this to now become just theta, I technically divide it by 2. And so over here, if this is already just theta, I had to divide it by 2 as well. And so this is just a modified version of this identity. And then we can plug that in. And so all I did was factor out a 2 from inside this square root. And that's why I was able to plug in for 1 minus cosine theta, this quantity, 2 sine squared of theta over 2. Okay? So the 2 in the very front here was from me factoring out this 2 right here. All right, and then we can go ahead and take this 2 times 2, and it is being square rooted, so that's square root of 4, and that's where this 2 in the front comes from. So I just took the square root of 4 from right here. And then what's left is we have square root of something squared. So that's going to undo the square. And we just have sine of theta over 2. Okay, and from here, we're just going to use a quick u substitution and then what the antiderivative of sine is. So sine, antiderivative is negative cosine, but we have this extra 2 in the front from using substitution. If you just let u equal theta over 2, then you're going to have an extra times 2 in the front here. Okay, and then we evaluate from 0 to 2 pi. And then if we plug that in, notice we're dividing our angle by 2. So when we plug in 2 pi, we actually divide and we just get pi. When we plug in 0, just get 0. And then cosine of pi is negative 1, so that becomes 4. And then cosine of 0 is 1. Final answer, 8. So 8 units. So this curve length, if we were to travel around this curve, we would be, let's just pretend we're walking, we'd be walking 8 units. Okay, so that's it for this one, you guys. See you next time.